The intersection of generative AI, computational engineering, and 3D metal printing is fundamentally reshaping aerospace manufacturing. For decades, rocket engine design was limited by what human engineers could draw in CAD software and what traditional CNC machines could physically carve out. Today, AI models are designing high-performance rocket propulsion systems from scratch, often in a matter of days or weeks, resulting in geometries that look more organic than mechanical. 1. The breakthrough, Leap 71 and Noyron. A primary pioneer in this field is Leap 71, an engineering tech company that developed Noyron, a large computational engineering model. Instead of relying on a human to manually position every wall and cooling channel, Noyron uses physics-based AI paradigms to generate complete, production-ready rocket engines autonomously based on high-level constraints, like thrust requirements, fuel type, and pressure. Key milestones: the 5 kilonewtons Aerospike, late 2024, Noyron designed a liquid fuel, cryogenic LOX and kerosene, Aerospike engine in just a few weeks. It was 3D printed as a single, monolithic copper piece and successfully hot-fired on its first attempt. 20 kilonewtons Methalarx engines, late 2025, the AI, autonomously scaled up to generate 2 orbital-class, 20 kilonewton methane liquid oxygen engines. The entire process, from initial specifications to final ignition on the test stand, took less than 3 weeks. The Meganewton Scale and Aerospike's 2026 collaborations are actively industrializing these AI-designed aerospace systems, scaling computational models to meganewton class thrust for next-generation spacecraft. 2. Why AI excel where humans couldn't. The Aerospike example. The classic, bell-shaped, rocket nozzle is highly efficient at a specific altitude but loses efficiency as atmospheric pressure changes. The Aerospike nozzle solves this by using a central wedge or spike, allowing the exhaust gas to automatically self-adjust to ambient pressure at all altitudes. While the Aerospike concept has been understood since the 1960s, and heavily researched during NASA's X-33 program, it was historically deemed impossible to safely implement due to 2 core bottlenecks that AI has finally broken. Extreme thermal management. The central spike is surrounded by exhaust gases exceeding 3,500 carat, circ, text, c. AI solves this by pathfinding hundreds of hyper-complex, micro-fine regenerative cooling channels curving through the interior of the metal. These geometries are mathematically optimized for fluid dynamics and heat dissipation in ways a human engineer could never plot by hand. Monolithic manufacturing. Traditional manufacturing cannot carve internal, winding, variable porosity cooling channels into a solid block of metal. AI pairs perfectly with industrial 3D printing, laser powder bed fusion, allowing these complex internal lattices to be grown layer by layer as a single piece of copper or nickel alloy. 3. The paradigm shift in aerospace. The combination of generative design and additive manufacturing has rewritten the playbook for space hardware. 0 to ignition in weeks. Traditional rocket engine development takes years and hundreds of millions of dollars. Computational engineering models compress the design loop to weeks or days. Rapid iteration. If a test fire uncovers a thermal hotspot or fluid anomaly, engineers don't need to rebuild a CAD model from scratch. They simply tweak the physics parameters in the AI model, and a corrected, optimized engine geometry is instantly generated. Radical weight savings. AI naturally utilizes topology optimization, putting metal exactly where stress dictates it needs to be, and leaving structural voids everywhere else. This dramatically lowers the overall weight of the engine, which is the holy grail of rocket science.